Hi, everyone. So this is the fifth module for the Bc32 Short Communications assignment. And as you can see, this module is all about presenting results. Now, of course, before you can present your results, you have to collect your data. And so as you know, you're going to be using HumMod, which is this computational physiology program, to run simulations of your experiment and generate data. What I want to emphasize here at the very beginning of this module is that, as it says here very clearly on the screen, HumMod is for data collection only. So HumMod, if you've played around with it, you'll know that it does create these kind of crude, rudimentary figures like you see here on the screen. We do not want you to be copying and pasting these figures into your short communications, okay? These figures that are in HumMod, they're really designed just to allow the user of HumMod to be able to quickly visualize the trends in whatever parameters they happen to be looking at. So what you see here on the screen, this pertains to an experiment that I talked about in one of the previous modules, where we wanted to see whether vitamin D supplementation had any kind of impact on testosterone levels in female participants. And so you can see here that the concentration of testosterone is being plotted in these very crude rudimentary figures by HumMod. We do not want to see you just copying and pasting those figures into your short communication. Okay. These figures, again, are really just for quick and easy visualization of trends for the users of HumMod. These are not publication quality figures. So our expectation for you is that you are going to use HumMod to get your data points. You can see here where it's telling me that the concentration of testosterone in nanomoles per liter is 0.4. So I'm going to extract those data points from HumMod, and then I'm going to use those data points probably through Excel or through Google Sheets or through some other piece of software to then present those data in a publication quality format. And I'll talk about how we do that in just a second. But again, I really just want to emphasize the point up there in that top right corner of the figure, top right corner of the screen rather. I want to emphasize that point that we should never see these HumMod figures just copied and pasted into your short communication. Okay, so what I want to talk about next is really how do you write a results section? And before I get into kind of the nitty gritty details, I thought I would talk a little bit more philosophically about how a results section is structured. And so what I have here on the screen is a couple of pages from a children's book. And the reason that I've put these pages up here is because when I think about how I approach writing the results section of a scientific paper, what I actually am doing is actually channeling my inner children's author, because the results section of a scientific paper is structured very similarly to a children's book. What I mean by that is that you have these two fundamental components. You have the text, but you also have the illustrations, right? So I can see here on these two pages the text, and I can see the illustrations. Similarly, when I'm looking at the results section of a scientific paper, I have text that I'm going to read, but there are also figures that are illustrating the data. And so I have these two components, and they're meant to be complementary to each other. Now, if I look here at the illustration in this children's book, I can see that there's some kind of, I think, dog maybe here, and it has a ball in its mouth. So I don't know exactly what it's doing with that ball. It could be playing fetch. It could be carrying that ball from one place to another. I can see that there are leaves falling down, and so I think it must be autumn. So, by looking at the illustration, I can sort of get a sense of what's happening here. But then if I glance over to the text on the other side of the book, and I start reading, it says Scooter has wheels that he calls his Scoot Scoot. Well, first and foremost, I hadn't even actually noticed when I was looking at the illustration, I had not noticed that he had these wheels on at the back. right? They kind of blend in with his body. The wheels are black. It's a black dog. They kind of blend in. So I hadn't really noticed that he had these wheels, but thanks to the text, it drew my attention to that. It continues to say he puts them on every morning, like you and I put on a boot. He loves to play fetch. So now I get a sense that that ball in his mouth is in fact about playing fetch and not just carrying or transporting the ball from place to place. He loves to chase after the leaves. So it doesn't tell me that it's autumn per se, but just tells me that the leaves are important to Scooter. So again, what I hope you're kind of seeing here is how by having both text and an illustration, the overall kind of richness of the book is enhanced, right? And I think it's very similar when you're looking at the results section of a scientific paper. If the results section simply had entirely text describing to you the results, I mean, you would understand what was going on just by reading the text, but you might get a fuller appreciation if you can actually see the illustrations of the data as well, if you can see the figures. And similarly, if the results section of a scientific paper was nothing but a series of figures, there would be a possibility, of course, that you might overlook some of what's happening in the data, in the same way that I overlooked the wheels here that Scooter was attached to. So when you're writing your results section, I would encourage you to imagine that you're writing a children's book and that you're trying to incorporate both text and illustrations, and they're meant to be complementing each other to allow for your reader to come away from the results section with a really full appreciation for the data that you have collected and are presenting. Now, to go into a bit more detail here, I'm going to examine just a snippet of the results section from this paper here. So the paper is called Suppression of Mitochondrial Respiration by Hydrogen Sulfide in Hibernating 13-Line Ground Squirrels. One of the reasons I chose to pick this particular paper is because one of its authors is my former PhD supervisor, Jim Staples. So I thought I could give a little shout out to Jim here for his role in kind of getting me to this stage of my career. So thanks, Jim. In any case, I want to start reading the results section here from this paper. And if you start reading it, the first thing it says is, we first measured bioavailable hydrogen sulfide in plasma and liver from winter and summer active 13-line ground squirrels to search for in vivo changes. Now you'll notice there are actually no results mentioned in that first sentence. What this first sentence is doing is it's actually providing a brief rationale for the study, and it's kind of summarizing the methods that were used. And that's perfectly fine. It's perfectly okay to have these brief summaries of your rationale and methods in your results section. You're basically just trying to contextualize the results that you are about to present. Okay? And so that's perfectly fine. It's also perfectly fine not to have this one sentence summary of rationale and methods either. If you want to just jump straight into the results, that's fine too. I mean, arguably you could say, hey, anybody who's reading my results hopefully has already read my introduction, so they kind of know what the rationale for this study is, and they've hopefully already read the methods, and so they understand how I collected these data. But again, it's not uncommon for people to skip the intro and skip the methods. You know, they may have read the title and they kind of have a sense of what this paper is about, and so they just want to jump straight into the results to see the data you collected. And so having these brief summaries of rationale and methods can be helpful. Again, I'm going to emphasize the word brief here and say that you want to strictly avoid rewriting your entire intro and methods in the results section. If you're going to include any kind of intro, background, or methods in your results, keep it to one sentence per paragraph, right? Just giving a very brief context to the results that are to follow. Okay, if we keep reading here, it goes on to say that plasma hydrogen sulfide levels were significantly higher in summer than in winter hibernating squirrels, where levels did not differ between torpor and IBE. And there's a reference there to figure 1A, so that draws my attention down to the figure, which I'll look at in a second. And then it also goes on to say, in the liver of 13-line ground squirrels, Bioavailable hydrogen sulfide was significantly higher in torpor compared with IBE and summer. And again, there's a reference to figure 1b. So I'm going to go down and check out the data in figure 1b. So again, I would say that Jim and his colleagues did a very nice job of writing this part of the results section. And if you notice what they did here in the results text is they used the text to guide the reader through the trends in the result. Okay. And that's actually really important to emphasize. That's why I've bolded the word trends here, because when you are writing the text section of a results section, the text component of a results section, you're meant to just be describing the trends in the data. You don't need to describe the actual data. So what I mean by that is you'll notice that if you reread this result section, it doesn't say something like plasma H2S levels were 6.2 micromolar in summer, but 1.3 micromolar in IBE and 1.2 micromolar in torpor. It doesn't actually give me any of the specific values within the text. It's simply describing the trends, right? What was higher, what was lower, what was different or not different. And so that's what you want to do in the text of your results section, is focus on describing the trends, but do not give the actual data points. The actual data points can be seen by actually looking at the figures that you've made, right? There's a general rule in science papers that you don't show the same data twice. So if I've got a figure that's showing me the data and the values, I don't need to restate those values in the text, okay? Now, if we go back to Jim's paper here, and we can also see how they're very descriptive in terms of how they actually mention the trends. I'll highlight, for example, this phrase here, significantly higher, okay? So the higher part is really important because they're telling me that the levels of plasma hydrogen sulfide were higher in summer than in winter, right? They're not just telling me that they were different, right? They're not just saying that there was a difference. They're telling me the direction, the nature of that difference. And that's really key, okay? So words like higher, lower, increasing, decreasing, positive or negative correlations, these kinds of words should be present in the text of your results section. We shouldn't be seeing just, oh, there was a difference. There was a difference. You'd be amazed how often, especially students, tend to write that way, where they just talk about everything as being different, and then I have to go to the data to be able to see the nature of that difference. Spell it out for me, right? Indicate very clearly what that difference is in the text component of your results section. Later on, you can see where they say did not differ significantly. So here we have, again, the torpor and IBE data that are the same in terms of their mean. So they did not differ. Okay, and that's a perfectly acceptable phrase to use as well, where there isn't a difference. So if there are differences, be clear about the nature of those differences. And if there aren't differences, then you can simply use the phrase did not differ or something similar. Now, I just want to talk briefly about the word significantly that appears here in the results text on the screen. Whenever you see the word significantly in the results text of a scientific paper, what that word is communicating to the reader is that some kind of statistical test was conducted to verify that the difference in the mean values between whatever groups we're comparing are actually likely real differences in the mean values, okay? So the word significantly implies that you did a statistical test and you got a p-value of less than 0.05. And what a p-value of less than 0.05 literally means is that there's a less than 5% chance that this difference in mean values you're seeing between your groups is just happening by chance, okay? So again, that word significantly, we're not using it haphazardly here in the results text of a scientific paper. It's actually communicating to the reader that you did a statistical test, the p-value was less than 0.05, and therefore we have a real difference, more than likely, a real difference between the groups that we are comparing in terms of their mean values. By comparison, when we see did not differ significantly, that implies that we did some kind of statistical test, but the p-value came back as greater than 0.05. And that tells us that we actually don't have a real difference in the mean values between the two groups that we're comparing, even if they might look different. Even if those mean values are different, it's not a real difference. It's just a difference we're seeing by chance. Let me just explain what I mean by that a little bit more. So if you look at figure 1b here, where they measured the liver hydrogen sulfide concentrations in the summer, the IBE, and the torpor state, you can see that when you look at the mean value for summer, it appears to be around, say, 55 or 60 micromolar. And when you look at the mean value for IBE, it definitely looks to be lower, down around 40 micromolar. So obviously, 55, 60 is different from 40, just thinking about things numerically. But what you'll notice is those were not actually considered to be a statistically significant difference. I know that in part because that's what they say in the text, right? In the last sentence of the text, they say that H2S was significantly higher in torpor compared with IBE and summer. So they're telling us there that IBE and summer were actually the same. But I can also see actually when I look at the figure itself, because you'll notice the letter A is above both the summer and the IBE bar. And this is one way that researchers will communicate statistical information on figures is they'll use letters, okay? And the basic idea here is that if two bars have the same letter on top of them, it means that those two mean values are not statistically different from each other. So again, even though we are seeing slightly higher liver H2S values in the summer compared to the IB, there's not actually a statistically significant difference in those values. They just look different here by chance. That's what is being communicated to us here. Okay, so that's an important thing for you to really appreciate, because one of the things that happens a lot in scientific papers, lab reports, etc., that students write is they'll often say things like, oh, the liver H2S was higher slightly in the summer than it was in IBE, but statistical analysis found that it was not a significant difference. You don't want to say that, right? Because you're basically saying, well, there is a difference, but there isn't a difference, right? And that's very confusing and contradictory. The stats tell you what is significant, and that's what you talk about, right? So we're either going to say something is different, higher, lower, whatever, because the stats gave us a p-value of less than 0.05. And if the stats gave us a p-value of greater than 0.05, then we are going to say that there is no difference, right? That in this case, just as I said here in the text, the IBE in the summer, they're implying in the way they've written the text that there's no difference between those values, but both those values differ from the torpor value, which is why when we look at figure 1b and we look at the torpor bar, we see a letter B sitting above that bar. That indicates to us that torpor and the mean value there, which appears to be up around maybe 80 or 85, is in fact really and significantly higher than the values that we're seeing in either the summer or the IBE case. Okay. Now, the next thing I want to mention here is that we are expecting that you're going to do statistical analysis of the data that you collect as part of this study. And I'm not really sure, what your level of statistical knowledge is. Maybe you took a stats course in first year. Maybe you've had to use statistics in some of the other courses you've taken. Maybe you didn't take stats. Maybe you took calculus and you've never done anything statistical. Certainly, we can help you with doing stats if you're not familiar with it. But here's the comment I'm going to make. So I pay for a subscription to GraphPad Prism. I basically use a small professional allowance that I'm given to cover that cost. But because I have a subscription to GraphPad Prism, the company that sells the software, they allow students in my courses to use the software for free. And so I'm going to mention right now that she should have gotten an email back towards the beginning of the semester with some kind of invite link to basically access your free GraphPad Prism account, which is free to you as long as you are a student in this course, and it actually expires when the course expires, so you can't carry it with you beyond the course. Um, but GraphPad Prism is a fantastic program for making not only professional figures like the ones you are seeing here on the screen, but also it has built-in statistical analysis tools that basically allow you to very quickly and easily analyze the data that you have given to the program and asked it to plot. So I will also mention that if you go back to the page for this module, just beneath where you accessed this video, you'll find a playlist, a YouTube playlist with a whole bunch of videos for how to do various things, including statistical tests within GraphPad Prism. That's what I would suggest. I mean, especially if you're completely new to statistics and you don't really have any sense of how to do it. You've got access to GraphPad Prism for the semester, and it's a really easy program to make plots and to run statistical analyses. Now, if you have familiarity making graphs in other programs, and you have familiarity running statistical analysis in other programs, by all means, if you have access to those programs, use them, especially if you feel comfortable with them. But if you don't have other programs that you have been making graphs in or running stats in, then let me strongly suggest using the GraphPad Prism program. If you find that you need some assistance doing stats or making figures, to be fair, GraphPad Prism is a program that I haven't used a tremendous amount. I'm still kind of learning it a bit, but I'm happy to kind of figure things out and pass that knowledge along to you. So don't hesitate to reach out to me if you're having any issues with either figures or making or conducting the statistical analysis. But again, I do want to emphasize that we are expecting that you are going to do statistical analysis of your data, and you're going to describe your data as they have done here, thinking about what the stats have told you. Are these differences actual, real, significant differences, or are they not? Now, one thing I want to mention here, which they did not do in the results text that you see on the screen here, is anytime you say that there is a significant difference or there is not a significant difference between the groups that you're comparing, you should always put the p-value either at the end of that sentence or right behind the word significantly. Put the p-value so that people know what that p-value is. And I would suggest that you put the actual p-value, not just p less than 0.05 or p greater than 0.05. Put the actual p-value. All right, and that way people know exactly how significant this finding is, right? Is it 0.048 and it's really close to that boundary of significance and non-significance, or is it 0.006 and therefore it's a highly significant finding? Your readers want to know. Now, what I will also note is that if your p-value is very, very small, then you can just say, p less than 0.01, for example. You don't need to give the exact p-value and use, some kind of scientific notation to convey your p-value. That's never the way that it's done. Now, the other thing I wanted to mention here is in terms of how do you present your statistical analysis on the figure itself. We've already talked about one way to do this, which involves using letters on top of the bars. And so bars with the same letters are not significantly different from each other, and bars with different letters on top are significantly different from each other. This is a very good way to present your statistical information on a figure, especially when you have, lots of different groups that you're comparing. And what you probably should do, and again, they didn't do it here in the caption for this figure, but it's always a good idea to just say in the caption, bars with the same letter above are not significantly different, p greater than 0.05, and bars with different letters above are significantly different, p less than 0.05. It's always a good idea to put that statement in the caption. The reality is anybody who is in science and who sees these letters above bars, they know exactly what they mean. So they're probably never going to actually read that sentence that you write in the caption. But it is a good idea and a good practice to include that sentence notwithstanding. Now, another way that you can present the results of statistical analyses on a figure, so here's a different set of figures that I found, is you can use asterisks. And so here you can see they're using kind of brackets with asterisks above them. So the brackets kind of show you which two bars are being compared. And then the asterisks above indicate to you that there's a statistical significant difference between those two values, between those two bars. And you'll notice that sometimes they use 1, sometimes they use 2, sometimes 3, sometimes 4 asterisks. And the more asterisks you have, the more significant the finding is. So basically, the lower the p-value is. And again, that's typically communicated in the figure caption. So here's the figure caption for this figure. You can see it says statistical significance labels, and then it gives us, NS is not significant, which is interesting that they mention that because they didn't ever use NS on this particular figure. 1 asterisk is p less than 0.05, 2 asterisks p less than 0.01, 3 asterisks p less than 0.001, and so forth. You get the point. So again, this is a very common way of showing statistical analysis results on your figures. GraphPad Prism for sure is able to do this. I imagine actually this figure was probably constructed in GraphPad Prism and it just sort of let it do it automatically. Again, one of the things I'll mention here is that if you are using the asterisks and these brackets and you're finding that there's like, dozens and dozens of brackets and asterisks and it looks kind of messy all over the place, I would strongly suggest at that point you think about using the letters, okay? Because the letters are usually a cleaner look if you have too many significant comparisons going on. So again, a couple of different ways that you can present statistical information on a figure. Okay. Okay, a couple of things I wanted to highlight here. Again, I mentioned this already, but you can see that each figure is referenced within the text section. So they told us that, plasma H2S levels were significantly higher in summer than winter, and they told us that we could see that data in figure 1A. And so now I'm going to go down to figure 1A, and I'm going to examine the actual data, because again, the text just told me about the trend, it being higher. Now I can see, by looking at the data, I can see how much higher it is. I can see all the individual data points. So you want to always make reference in your text section to every figure within your paper. And that, again, is just going to direct people to not just read the text, but it's going to direct them to where they can actually see the corresponding data. Okay, you don't want people guessing where they can see the data that corresponds to statements that you've made in your text. You want to use the reference to the figure right in the text so people know exactly where to look. I'll also emphasize, as it mentions here, that figures should always be numbered in the order in which they are mentioned in the text. So the plasma hydrogen sulfide levels are figure 1A because they're the first result mentioned, right? And then the liver hydrogen sulfide was the second data set mentioned. So the second figure mentioned. And so that's why we call it figure 1B. Had Jim and his colleagues decided to flip the order and talk about liver first and plasma second, then they would have had to make the liver figure 1A and the plasma figure 1B. So you should always organize your figures in a way that reflects the order in which those figures are mentioned within the results section. Hopefully that's clear. Okay, we've examined the text to death now, so let's have a closer look at the figures themselves. Again, you can see here that they've got a multi-panel figure here. It has 1A and 1B. As it says, it's perfectly fine for figures to have multiple panels like this. And indeed, you do this when the data are related to each other in some way. So in this particular case, both the figures here deal with hydrogen sulfide concentrations. And so that's the relationship that exists between them. And so in that case, it's perfectly justifiable to put these two figures together as multiple panels within the same figure. And actually, it's probably the preferable way to do it. You could have made this, figure 1A here could have just been figure 1, and then you say, okay, well, figure 1B will just be figure 2, and then I have separate figures. But if there's some kind of relationship between the data in your figures, then usually people will cluster them into a single multi-panel figure. If they're not related in any way, if we were showing plasma hydrogen sulfide and liver nitric oxide or something, and I can't see any kind of relationship between these two data sets, then it makes more sense to present them as separate figures. And then lastly, I want to talk briefly about figure captions, which I can see actually has been a little cut off here. But you should always have a figure caption for any figure in your short communication. And the figure caption should always appear below the figure itself. That's the customary location where we put figure captions. And if you look at the way a figure caption is structured, so it starts obviously by saying figure 1, so we know this is figure 1. But then you'll notice that the first sentence of the figure caption is essentially the title of the figure. In this case, it says in vivo H2S levels and H2S induced inhibition of mitochondrial respiration. And in fact, they've italicized it here, I guess, to really emphasize that it's a title. So the first sentence of your figure caption should be a title. And correspondingly, you should not have a title appear anywhere else on the figure. I mention that because oftentimes with, say, Excel, it always tries to put a title at the top of your figure, and that's not necessary, nor actually is it the common style in scientific publications. So have your figure, no title above it, and the first sentence of your figure caption is going to be the title. And then you'll notice that they go on here to describe what I'm seeing in each panel of the figure. Now they've actually combined A and B together here. There's actually more to this figure than I've showed, but I didn't want to show everything. But you generally will go on to describe what am I seeing in each of these panels. And again, if you just kind of read what they've written here, it says hydrogen sulfide levels in plasma and liver of summer and winter ground squirrels. It doesn't tell me the trends. It doesn't tell me anything about the data, right? That's the job of the text component of the results section. It's not the job of the caption, right? The caption is not going to tell me about the trends. It's not going to have data values in it. It's simply going to tell me what am I looking at. And then unfortunately, the part that got cut off here is it says individual values are shown with mean plus or minus standard error of the mean. And so that's a very important part of the caption as well, right? It's very important that you tell people, that the bars represent the mean value. You tell them what your error bars are showing, in this case, standard error of the mean, because there are different kinds of error bars. Sometimes you show standard error of the mean, sometimes you show standard deviation, sometimes people show 95% confidence intervals. It's important that people know what specific kind of error bar are you showing. So you need to make that clear. And I would actually go a little bit further than Jim and his colleagues did here. They said individual values are shown, but I might have been very clear and said, the filled dots show the individual values, something along those lines, just so I know very clearly that those are what the dots are doing. Now, I think we're at the point now where you could figure that out, but it never hurts to be more explicit rather than less explicit. Okay, so now we have a bit of a sense for how to put the result section together. I want to spend a little time talking about a concept that is really becoming a bigger and bigger force within biology especially, and that's the concept of data transparency. So what I have here is a bar graph, and this is a bar graph like you might see in a lot of scientific papers. This bar graph, let's say the two bars represent the sweat rate of males and females during exercise. In one of the previous modules, we had talked about an experiment where we were going to measure sweat rates of males and females during exercise. So I have a bar graph here. The dark bar is showing me the male sweat rate, and the white bar is showing me the female sweat rate. And of course, the height of the bar corresponds to the mean value that was measured for all the data points. And we have an error bar, which in this case is the standard error of the mean. Now, These two values, the mean and the standard error of the mean, these are what are known as summary statistics, right? Because what they are doing is they are giving us a summary of all the data that was collected, right? They're telling us what was the mean value for all the male and female sweat rates and what's the standard error of that mean. So they're summary statistics. And for a long time in science and in biology, when you would look at scientific papers, this is all you would get, is you would get the summary statistics. And the problem with just seeing the summary statistics is, as the rest of this figure now illustrates, different patterns of data can give rise to the exact same summary statistics. So I've got here 4 so-called dot plots now. So each dot on these plots corresponds to an individual data point that was measured in the study. And for all these 4 dot plots, which you can see at a glance all look different from each other, they all give rise to the same mean and standard error of the mean. And so they all give rise to that same bar plot that you see in part A of the figure. And so right away, I think you can see that there's a problem with just doing traditional bar plots and just showing the summary statistics. And the problem is that those summary statistics can be hiding the fact that the individual data points are perhaps giving different kinds of patterns. So if I look, for example, at panel B here, which they label as symmetric, I can see here that for my males and my females, I can see there's variation, obviously, in the data points that were measured, and that's not surprising because I do have error bars in my plot. But I can see now that generally the female points are all kind of shifted upward, shifted to a higher sweat rate than the male points. And that's probably what I would have envisioned, right? If I was thinking about this bar plot here and I kind of envisioned what the individual data points looked like, the symmetric plot is probably what I would have been envisioning in my head, right? That all the data points for the females are kind of shifted to a higher level than the data points for the males. But now let's look at panel C. In panel C, which again gives us the same means and same standard errors as panel B, panel C looks very different because now I see that the majority of the data points for the males and females actually overlap one another. And we have this one single outlier data point for the females that's way higher than the rest. And that's what's causing the mean for the females to be higher than it is for the males. And so that wasn't what I was envisioning in my mind when I saw this bar plot. And I would argue that the conclusion you're going to reach from this data set is very different if your data are like panel C compared to panel B, because with panel C, I'm thinking, well, it looks like it's just one outlier data point that's kind of making it appear the females have a higher sweat rate. I don't think there's any difference in sweat rate among the sexes. There's just this one outlier. So this is where showing me individual data points and being completely transparent with your data is a good idea. Plus, on top of that, if you as the researcher are just so accustomed to calculating means and standard errors and making bar plots, and you don't actually take a careful look at the individual data points either, you might miss the fact that you've got this outlier-driven difference rather than perhaps a real difference. So it's not only important from a transparency point of view to our readers to see all the data points, but it's actually a good practice for researchers as well to ensure that they are actually looking at the distribution of their data points and not just summary statistics. If we go on to panel D here, which says bimodal, you can see here that within both the males and the females, we do seem to have a bimodal distribution of the data. Some of the sweat rates are higher and some of them are lower. And again, that's kind of an interesting thing. It makes me think that, maybe there are some people who sweat a lot when they exercise and others who don't sweat as much. And maybe that wasn't central to my research question, but it's got me thinking about possible future research questions I could be asking. Why do some males sweat more than others while exercising? Why do some females sweat more? And if I look at panel E, it focuses here on unequal N. Here I can see very clearly that there are twice as many data points for the males as there are for the females. Now, again, you might say to yourself, well, even if I was just doing a typical bar graph, I would generally indicate the sample size in the figure caption. So I would have said, n equals 10 for males and n equals 4 for females in the figure caption. And so it would have been very clear to the reader that there was an unequal sample size, and that's true. But sometimes people do gloss over that. And it's not something you want to gloss over because, you know, depending on, again, the kinds of statistical tests you're doing, and again, I know that's irrelevant for the short communications because we're not asking you to do stats, but not all statistical tests work well when there's unequal sample sizes. And so again, when you are a researcher and you kind of remind yourself that, oh, I have very unequal sample sizes, then you have to do certain kinds of statistical tests and not others. And as a reader, you want to assess by looking perhaps at the statistical analysis section of the methods, have these researchers actually use an appropriate statistical analysis to account for their unequal n. So again, the point I'm trying to make overall here is that by having dot plots, we are able to, number one, as researchers, ensure that we've actually thought about the distribution of our data. And as readers, we are able to see every individual data point and therefore better evaluate the conclusions being drawn within the paper. Now, what I would suggest, and this is the direction that biology is moving, and actually, I'm not going to just suggest it, I'm going to say it's a requirement for BioC32. What we want you to do for BioC32 when you're preparing figures is we want you to use these combination bar dot plots like Jim Staples and his colleagues had used in the paper I was showing you before. So again, the beauty of these plots is that they show you both the summary statistics, which people want to see, but they also show you the individual data points that contribute to those mean and standard error of the mean values, which then allows people to see the distribution of the data, to better evaluate the conclusions that the paper is making. And so this is the direction that biology is going for sure. If you thumb through the pages of any recent biological journals, these are the kinds of plots you're going to see in growing number. And so we ask that you use dot bar plots for your short communication. Now, if you're not sure how to make these plots, there's actually a link posted underneath this video in the module. It takes you to a YouTube video where they walk you through step by step how to make beautiful dot bar plots within Excel. So check out that link and you'll find yourself making these beautiful dot bar plots in no time. One last point I want to mention about these plots is the concept of jittering. So again, this idea of data transparency and making sure that everyone can see all the data points, you'll notice when you look especially at the IBE or especially the torpor data here, all the values are very similar, right? All the plasma H2S values are very similar. So there's a potential for them, if you kind of plot them all at one X value on the X axis, that they would all overlap each other. And then I wouldn't necessarily be able to see all the individual data points. So you want to make sure that you do what's called jittering, basically that you kind of spread your data points out along the X axis so that every single one of them can be seen, at least to some extent. You can see there's still some overlapping points in this figure, but that's fine. I can tell that there's 1, 2, 3, 4, 5, 6, 7 individual data points there, even if I can't see the entirety of all data points. So kind of think of this akin to when you're taking a family photograph. Let's say you're visiting all your extended family for a holiday and you're going to take a big family photo. You wouldn't want your grandmother to be buried in behind your grandfather so that you can't see her and you don't know she was there. Because then someday down the future, you're going to be looking at the picture and thinking like, was grandma even at this event? Was she not there? Had she passed away by this time? Was she, what was the deal? Well, she was actually there, but she was blocked in behind. So you don't want that to be the case. You want to know grandma was in the family photograph. You want to know that every data point is accounted for. Make sure you use jittering to make data points visible. The next thing I want to briefly talk about here is I want to spend just a little time talking about outliers. And I want to do that because I think that the kind of classical historical way that biologists have thought about outliers is very outdated. I remember when I was going through grad school as an example, and we would get data sets. And if we had one or two outliers in our data set, it was very common that we would do a statistical test to verify that it was an outlier. And if it was, we would just throw those data points away and say, oh, they're outliers. They're going they're not good data points. Let's get rid of them. I think that's a problem. And so what I would say is we need to change the way we think about outliers in our data. And really the question we have to be asking ourselves when we see outliers in our data is, why are they there? And the first thing you can ask yourself is, did something known go wrong? That is to say, is this an outlier data point because something I know happened while collecting that data point that makes it suspect? Again, thinking about male and female sweat rates, for example, I have these people exercising for 20 minutes maybe, and I collect their sweat over that 20 minutes. Maybe that day I know that it got collected for half an hour instead, and that's why it's higher. Okay. If I know that there's some problem with that data point, right, a known problem, then I'm free to omit it. Because if I know there's something wrong with it, I know that it doesn't really fit in with the other data points, then I should omit it. But if I don't know that there's something wrong with that data point, then really the first question I should ask myself is, well, how much of an influence is this outlier having on my data? In the context of this study we're looking at, it looks like it's having a big effect, right? It's that one outlier that's causing the female sweat rate to have a higher mean. If you got rid of that one data point, I think the means would be pretty much the same. So I think the answer to the question in this case is it's having a big effect. And as it mentions here, the effect usually depends on the total sample size. If you have one outlier in a sample size of 7, it's going to have a big effect, whereas if you have one outlier in a sample size of 70, it won't. So what I would suggest when you have outliers, and again, you don't know that you can get rid of them because they're not, there's no known issue, what I would suggest that you do is you run your analysis, your statistical analysis, both with and without the outlier. And if you get the same results at the end, that there's a difference, then fine. You just leave the outlier there and you know it's not a problem. If you get different results, it's significant with the outlier, but not significant with it, or vice versa, then you're going to probably, the best practice in that case is probably to just lay that out right in the results. You can say in the results, look, we have this one outlier data point. We did the analysis both with it and without. Here's what we got with it. Here's what we got without it. I think it's fine to, again, from a data transparency perspective, you're just kind of laying it out for people and let them kind of figure out what they want to make of that outlier and its impact on your results. Okay. I think, again, the reason that we have historically thrown outliers out very easily is because we've historically not wanted our data sets to be messy. The thing that scientists seem to hate the most is when they get data sets that are just messy. You get that one outlier and you're like, well, what do I do with this? What kind of conclusions can I reach? And so sometimes there's a temptation to say, look, if I just throw the outlier away, it simplifies my life. It makes it clearer that there's no difference and I can just talk about that. But I think we have to remember that, again, as researchers, our goal is to actually understand what's going on in the world around us. And what's going on in the world around us is the world's a mess, right? The world is just full of variation. And so we have to, I think, as researchers, embrace that. Of course, another thing you could do too here is you could say, can I add more data points to this study? Again, in this panel C that we've got pictured here, I mean, they've only measured 7 total females. And so that one outlier is having a big effect. Can I measure another 7 and see if I get more outliers? If I do, then that might start to lead me into the second point here, which is, do these outliers offer any insight? I mean, that's the thing too we should think about. If I look back to maybe my patient data and I think, well, is there anything different about this patient who's got the really high sweat rate compared to the others? And maybe I find out, oh, this patient was the youngest of the group. She was only 20 and all the other patients were kind of, 25 or up. Maybe there's an age effect in terms of how we respond to sweating during exercise that I wasn't even aware of, and now I start to explore with a future study. So again, I really just want to emphasize here that outliers, we should not be too quick to throw them out of our data sets. We should really try to understand what influence they're having on our data, if any, and the potential that they might open the door to new important understandings of concepts that we weren't aware of before. All right, the next thing I want to talk about with respect to making these bar dot plots is I want to talk about the y-axis. There's a bit of controversy around y-axes. When I was first learning how to make graphs, I remember having a teacher who was adamant that whenever you make a bar graph, the y-axis must always start at 0. Okay? She was adamant about this. And the reality is that that way of thinking about the y-axis, again, is kind of falling out of favor, generally speaking. The problem with starting your y-axis always at 0 is it creates what they call here on this figure a zone of irrelevance. And so what they mean by that is if you start the y-axis at 0, but maybe your first data points are at a y value of 10, well, now you have this whole range of your y-axis from 0 to 10 that doesn't encapsulate any of your data points. That's why they call it the zone of irrelevance, because there are no data within that range. The other thing that people very commonly do with their bar graphs, especially if they're just doing standard bar graphs with just the mean and the error bar, is they will often end the y-axis at a value just above the tip of that last or that highest error bar, as you can see here in panel A. And the problem with doing that is it creates something called the zone of invisibility, where you've stopped your y-axis at this point just above your highest error bar. But if you look over at plot B, you notice there are actually data values that go above that top of the y-axis. So that creates this zone of invisibility where you essentially have data points that are not being reflected in your y-axis. So again, here is the way that we should probably be doing our y-axes, and this is what we're going to ask you to do for the short communications. You should start your y-axis at a value just below your lowest data point and take it all the way up to a value just above your highest data point, just like they've done here in panel B on the slide. Okay? And so in that way, you get rid of the zone of irrelevance, you get rid of the zone of invisibility, and you also ensure that your y-axis then a reader could look at your y-axis and they could immediately know what range of data values you measured in your study, because it ranges from roughly the bottom of the y-axis to the top. So this is what, again, this is the kind of direction that we are moving as biologists in terms of data presentation, is making sure that our y-axis values are actually useful. They show us the range of observed values in the study, and we get rid of these zones of irrelevance and invisibility. Okay, the last thing I want to talk about here is scatter plots, because scatter plots, which have a long history in biology and other sciences, they are inherently good for data transparency, because the way we make a scatter plot is we show every individual data point on the plot, like you see here, okay? So this is another kind of plot you can make. Obviously, it only works when you have two continuous variables, so two variables that can take on any value. If you've got one continuous and one categorical, like we did with the males and females and their sweat rates, then obviously you can't do a scatter plot for that. You have to do a dot bar plot. But if you have two continuous variables, then you can do scatter plots, and they are good for data transparency. Every individual data point is visible on a scatter plot. Now, one of the other things you should do with scatter plots, and they do it here in this particular figure, is if you have different, what we call pre-hoc groups. So basically, pre-hoc groups are essentially treatment groups that you set up before the experiment began. Okay, so in this case, they had a control group, they had an EAE group, not really sure what that is, but it doesn't matter, and they had an EAE plus treatment group. Okay, so they had these 3 different groups that they established before they started collecting data. If you have pre-hoc groups like this, then you should do exactly what they've done here on this figure, and you should plot the data for each pre-hoc group separately from the others, and then have a separate regression line, a separate line of best fit that goes through the data for each separate pre-hoc group. And the reason to do this is it allows you to understand whether the relationship between the 2 parameters you're looking at, in this case, OCT thickness and perg amplitude, which again, I don't know what the hell these things are, but it doesn't matter. You get a chance to see, does the nature of the relationship between these 2 parameters differ among my different pre-hoc groups? And here, in fact, you can see it did, because for the controls, we see that the regression line is flat, right? So we see that basically OCT thickness is having no effect on perg amplitude in the controls, but there's a positive relationship for the EAE and EAE plus treatment groups. They seem to show a positive relationship between OCT thickness and perg amplitude. So again, if we had just plotted all the data points as one massive scatter plot and didn't separate them, we might have missed the fact that the controls and the 2 EAE groups are responding differently in terms of that relationship between OCT thickness and perg amplitude. Okay, so whenever you're making scatter plots, if you have different pre-hoc groups, you should put all the data into a single scatter plot first and foremost, as they've done here, because that'll make it easier to make comparisons among the different groups, but have each data set plotted as a different color with a different regression line or line of best fit plotted through it, and that will make it easier for you to see if there are any differences between your groups. Oh, actually, there's one more thing I wanted to mention here, which is to say that from a data transparency point of view, tables are often useless. And it says here, especially when you have 2 continuous variables. So here we have 4 tables, and they're showing us X and Y values, which according to the legend on the side, the X value is a person's age in years, and the Y is their middle finger length in centimeters. And so we have these 4 different tables, and you can see that there's 4 different data sets here. But when you look at the summary statistics at the bottom, all 4 of these tables, all 4 of these different data sets, they give rise to the exact same mean and standard deviation and R values, which of course R values are a measure of the strength of the correlation of the data. So all 4 of these different data sets give rise to the same mean, standard deviation, and R value. But interestingly, if you were to plot these 4 different data sets, they all look very different when they're plotted. You know, the first data set shows us a very linear relationship. The second data set, we actually have a parabolic relationship, not a linear one. The third data set is again linear, but we can see there's one outlier in the data set that's maybe causing the slope of the line to be higher than it otherwise should be. And then in the fourth case, we can see that the majority of our participants were all the same age. And we had one older participant who had a longer middle finger. And we start wondering, well, is that the reason we're seeing kind of a linear relationship here? Is just because, again, of this one data point. So again, the tables, you could say to yourself, look, I was being very data transparent because I showed you every individual data point I collected in the table. But the problem is that without plotting that data, we aren't able to really clearly visualize the complex relationship that might exist between these variables. So again, I would say that for your short communications and really for any scientific publications you're doing in the future, avoid tables wherever possible and always plot your data in some kind of data transparent manner. In this case, by plotting the data rather than putting it in tables, we were able to better visualize the relationship between age and middle finger length, and therefore had a better appreciation for how those two parameters relate and what's going on than if we just had the tables. Okay, so we end here with a bit of a summary of what you're going to be doing for this module. So obviously this module is going to be the results section of your short communication. You're going to, as I mentioned right at the very beginning, you're going to first execute your study using HumMod and collect your data from HumMod. Okay, so before you can even start thinking about plotting data, you have to run the experiment on HumMod and collect your data. For your submission, you have to have a text section as well as figures. So you're creating a proper result section with both text and figures. Your figures have to adhere to the data transparency principles we've discussed in this module. So again, the idea is that you want to be showing all your individual data points, and that can be done either with box dot plots or scatter plots. And make sure that your y-axis, and I guess also your x-axis labels, if you're talking about scatter plots, make sure that they again conform to this notion of we don't want zones of irrelevancy, we don't want zones of invisibility. So make sure that you are making your x and y axes proper in terms of their scaling. All your figures should have a detailed caption below them, and we talked about how to write figure captions at the beginning of this module. First sentence of the caption is a title, just describing what the data are, not the trends. If you're showing a data transparent kind of figure like you're expected to, then you don't necessarily have to tell me what the sample sizes are in the captions, but you still could, just to make it so that people don't have to necessarily go and count the dots. There won't likely be any additional references, so we're not expecting a reference section in this module. As I mentioned back in module 1, talking about citations, the results section of a typical scientific paper really just is a presentation of the data that was collected within that study. So there usually isn't going to be anything to make reference to. Now, there are sometimes exceptions. So you may have a reference or two, that's possible, but generally speaking, you won't require any references for the section. And then, as has been the case for the previous modules, you're going to submit this on Quirkus. The TAs will evaluate the work you've done, and if they're happy with it, they'll approve it. And if they think there are some problems with it, they will reject it with their feedback, and you'll have an opportunity to fix up your submission and resubmit it for re-evaluation. Okay, so I want to stop there. So what I'm hopeful at this point is that you are super excited to actually start kind of running HumMod and generating data. This is kind of the exciting part of science now, right? It's like, it's exciting to come up with questions and it's exciting to plan out the experiment. But the real excitement of any scientific study begins when you start collecting the data. And then I guess the real excitement comes at the end when you actually compile all that data, create figures, maybe do your statistical analysis if you're going to do that, and then start to say, oh, all this work I had done, and now I actually see that there's some interesting trend here that's either consistent or not consistent with my hypothesis. And yeah, that's where all the fun in science is. I can tell you from having from being involved in experimental work, I used to have this when I was a grad student. I used to say it especially that science is 9 terrible days to get to one really cool day. And what I meant by that is when you're actually in the trenches and you're doing the experimental collection, it's sometimes long and it's tedious and things happen along the way, and you're going to experience that firsthand with HumMod. That you're going to be sitting there, pushing the buttons and writing down the values, and it's going to feel like, oh, this is kind of tedious stuff. But then you get to that end day where you have all that data and you compile it together and you go, oh, there's some kind of cool thing happening here that I'm excited to talk about. Like, that's where the excitement of science comes from. So I hope that you will kind of feel that excitement to some extent as you are running through HumMod, and then as you are creating your result section with your figures. And so with that, I will stop, and I will see you in the next module.